So these notes are more about sound and some things that can happen due to interference and waves interlapping. So you've all heard of the Doppler effect, right? You know, you hear on the weather report that according to the Doppler. So Doppler, and this is important, that it's an effect. It's not a true change, right? It's due to motion, right? Due to relative motion. So it's a perceived change in sound. So this first picture right here is supposed to be like a bug. Imagine a little ladybug and she's bouncing up and down the water. And you've all seen this wave pattern, right? Where you just see interchangeable waves. So she just stays there and she makes one wave after another wave after another wave. Then it just looks like concentric circles. But now let's imagine she moves at some speed v and she moves towards B, right? So she's going from A to B. So if I am standing right here and I'm looking at those waves are coming at me. And notice what happens to the wavelength. If you look here, they're all squished together, right? And so the lambda is going down. That means I'm going to hear a higher frequency. So the frequency is going up. On the other hand, if I was on this side and she was moving away from me and I was looking at the waves, I would notice that the wavelength was going up because you can see them spreading apart and the frequency is going down. So I'm not going to hear them as often or see them as often if it's just a water wave, right? So this is for all waves. It works for sound waves, water waves, but that is the Doppler effect, is basically as you move due to this relative motion, you have this change in wavelength. Now, if she moves to the point where she's moving at the speed of the wave, so the V of the source is equal to the V of the wave. So this is the source, which would be the ladybug in this case, and this would be the wave. And so if the speed of the wave, because remember, the speed of the wave changes if you change mediums. So if it's in the same medium, it's going to be the same speed. So if she starts going faster, I think this is actually an airplane picture, but same concept. She starts going faster to the point that all the waves are overlapping right here. So you're going to get constructive interference here, right? We talked about constructive interference. Constructive interference there. And so that's going to become like this big wave in front of it, which is known as a bow wave. Let me erase just a little bit there so you can read the word. That is a bow wave, right? And so the wave is moving at the same speed and they're just overlapping. If, on the other hand, the object starts going faster so that the V of the source, this is the airplane or the ladybug, is greater than V of the wave, notice that overlapping happens now back here. So you're still getting this constructive interference, right? Here. It becomes kind of this cone shape going behind it, but that is known as a sonic boom or a shock wave. So you hear this loud boom afterwards. If you've ever tried to take a towel and whip it, you're making a sonic boom. If you take an actual whip and you hear that whip sound, the very end, the very tip of the whip is making a sonic boom because the whip is coming up and it's kind of going like this and it flies back and forth like this. And if you can get this little tip to go faster than the speed of sound, you get a sonic boom and you get a really loud sound. So here it is written nice and neatly. Doppler effect is the apparent change in frequency due to motion. So note the speed of sound stays the same. And the other thing to remember is that if it is moving, here it says small wavelength, high frequency when it's moving towards you. This would be a police car. And long wavelength, low frequency if it's moving away from you. Right? Because you can see this moving away from you. This is also known, this word drives people nuts, it's called receding, like a receding hairline. So if it's receding from you, it also tells you what's it makes the same thing, right? That's the same as a wave. That's how they use Doppler to figure out which way the storm is coming. They look at the light, which is a type of wave, and if they see it shifted one way or shifted another way, that is if the wavelength is smaller than it's supposed to be or higher than it's supposed to be, they know if it's coming towards you or away from you. It's the same reason you know whether to jump out of the way when you hear a siren. You can tell when it's coming towards you. You hear that higher frequency. The other thing that can happen with interference is something called beat frequency, which is due to interference of two waves that are very close to the same frequency. So here's frequency 1 and here's frequency 2. And when they come together, they make this bigger wave that your ear actually hears. And so you hear this like wobbling sound, kind of as you have constructive interference and destructive interference. So when you're tuning an instrument, you try to get that frequency to get as low as possible because it's the difference between them, right? And when there's no difference, that means that it sounds like one note. So it starts far, it starts far apart, and then it gets closer and closer to being the same note. And once you hear no wobble in the tone, you know you have a perfect tune. That's how people tune their instruments. So beat frequency, you want to put this on your equation sheet, is FB equals F1 minus F2. Notice it's got absolute value. So that means if this was equal to 150 hertz and this was equal to 148 hertz, then my beat frequency would simply be the absolute value of 150 minus 148, right? But it's absolute value, so it's just 2 hertz. If they get too far apart, your ear just can't hear it, right? So you can hear 2 hertz, you can hear 3 hertz, you can hear about to 10 hertz, but once it gets higher than that, you can't tell.